At University of Manitoba, and she will talk about optimal approximant and orthogonal polynomials in several variables. Meredith.
Hi all, thank you all for sticking around. I'm going to be talking about optimal approximants and orthogonal polynomials in several variables. This is joint work with Alan Sola at Stockholm University. We've got a couple of things that we've done with this, so I'm going to kind of try to give an overview. If you saw Catherine's talk last week, you already know a little bit about optimal approximants, but I'm going to start at the beginning anyway, hopefully. Okay, so what are optimal approximants? Well, okay, let's say we've got ourselves a Hilbert space, H, and I want to have a function in there, but 1 over that function might not be in the space. So an example of this is 1 minus z. That's definitely in the Hardy space of the disk, but 1 over 1 minus z is not in the Hardy space of the disk. So you can do partial Taylor sums, Calc 2 style, just write out your Taylor sums, lop off the first however many terms, sweet. But this might not give the best approximation, and we have to be kind of careful about what we mean when we say best here. Now, when I say best, I mean best in norm. So I'm going to try to find a degree n polynomial that minimizes this norm. You can think of this, okay, it's sort of like approximating 1 over f, but you could also think of it as approximating 1 in f times Pn. Now, Benito, Havenson, Leah, Secco, and Sola in 2016 showed that, okay, you can just get yourself an orthonormal basis in a weighted space, because remember I said this f times Pn, that's f times polynomials. Here's this weighted space where the only thing I'm doing is saying when I do my inner product, I'm going to be multiplying by the function. And we know from linear algebra that you can just write this out using your orthonormal basis, just with the inner product. And in fact, this then says, okay, well, I could gather my orthonormal polynomials here by looking at differences of my optimal approximants. So there's this nice back and forth relationship between the two. Now, of course, this depends on f phi n being nicely behaved, but hypothetically, this could work. Now, in several variables, we've got some more difficulty here. I have this as questions of degree. And the reason is because when we look at total degree in several variables, we can say, okay, total degree 1, we have z1 and z2. And I'm just going to do this in the 2 variable case. And total degree 2, well, we get a whole bunch more terms. So before I was talking about, oh, I want to find a degree n polynomial that does this approximation. Well, now, do I think about degree this way? There's also the option of thinking about it in terms of multi-degree. I want to be thinking about, okay, well, what's the degree on each variable? And here I've just written out multi-degree 1, 1 and multi-degree 2, 2. And you'll notice, again, I'm getting a whole bunch more terms when I do this. This is going to end up causing us problems. Because, for example, remember how I said that we want to be able to recover the orthonormal or orthogonal polynomials by looking at a difference of optimal polynomial approximants? Well, since they would be an orthogonal set, or an orthogonal basis, really, you should be able to build any element of the set in terms of those orthogonal polynomials. Well, just the basic function z1 here, that's definitely in this weighted space. I'm just looking at the Hardy space weighted by a nice simple function 2 minus z1 minus z2. It's definitely in there. Its norm is bounded. Awesome. But there's no way I'm going to be able to build z1 by looking at a difference of these things. If I do my p2 minus p1 here, well, I'm going to end up with lots of things floating around. I'm not going to be able to build a z1 out of that. And same thing with our multi-degree here. There are too many new terms added each time. I'm not going to be able to just build z1. So we need to come up with another way to look at this and another way to think of this kind of degree. It turns out one solution you can do is to choose a monomial ordering and build these things one monomial at a time. So instead of saying, okay, I want degree 5 or whatever, I'll say, okay, I want the first 5 monomials. So, and then I'll define my Pn. Before this was polynomials of degree n. Now this is going to be the monomials 0 up through n. We found it kind of enlightening to lay out our monomials this way when we did this in 2 variables. So here you read the monomial ordering down each column and then going left to right. This ends up being useful later, and I will hopefully be able to show you. But going back, whole reason we want to have this monomial ordering is because I want to be able to say, okay, I want to do the same projection. That's exactly what we were doing before. It's exactly what you do with your linear algebra students. You say, I want to find the closest point. Well, how do I do that? I do an orthogonal projection by taking the orthonormal basis. So we can find our optimal polynomial approximant. I'm pretty sure this should actually say f times Pn. Yeah. But you can still find your optimal approximant by just doing this projection. And it will give you, that's how orthogonal projection works, that will minimize this norm. Now, there's a way to compute, like actually compute these using matrix methods. And this is the method that we use to actually compute some of our examples. This is kind of a reinterpretation of some previous results. In our work, Alan and I do this for a somewhat general reproducing kernel Hilbert space. We require the reproducing kernel Hilbert space to be on a region containing the origin, and we later ask that the monomials are orthogonal. But you can say, all right, just build yourself a Gramian and solve this matrix equation. It's really nice. It does allow you to compute things. In particular, we can look at a specific case of spaces. We'll look at Dirichlet-type spaces of the Bidisk. So Dirichlet-type spaces, this is one that includes the Bergman space right there. I'm trying to stay on theme. Dirichlet-type spaces, these are things that you just say, all right, build the norm. This way, the inner product is defined similarly, where you weight it by alpha 1 and alpha 2. Now, usually we're interested in spaces where alpha 1 is equal to alpha 2. And in particular, we're looking at alpha equals 0, that gives you the Hardy space, alpha equals -1, that gives you the Bergman space of the Bidisk, and alpha equals 1, that gives you the Dirichlet space of the Bidisk. There's a whole range in here, but these are the ones we're familiar with. Let's do an explicit example. This, I'm just using the matrix method to compute the first few optimal approximants to 2 minus z1 minus z2. Now, part of the reason I'm looking at 2 minus z1 minus z2 is because it's kind of an obvious analog to 1 minus z, that very first example I showed you all. It's got a nice 0 on the boundary, pretty straightforward. So in the past, I've shown people this in terms of the Hardy space, but this is Bergman space week. So I have computed the first few optimal approximants to 1 over f in the Bergman space. And you can notice that when we've got full total degree is what I've been calling it, you have everything of degree 1, or here's everything of degree less than or equal to 2. Things are a little bit nicer. In general, these are going to be pretty symmetric because we're starting with a symmetric function, but you can compute these. I have a program where you hit go and it will compute however many your little heart desires, but you can figure these out. Now, one thing that we found that was kind of interesting when we were computing all of these examples, way back when we were first getting started, is that for this 2 minus z1 minus z2, well, I just said that's a 2 variable analog of 1 minus z. And Benito, Condori, Leal, Sacco, and Sola found that in the 1 variable case for 1 minus z, the coefficients for your optimal approximants are positively weighted sums of Taylor coefficients. So it's just kind of a modified Cesaro mean. Now, in the 2 variable case, some of our coefficients ended up being negative, and we were very confused by this, and I'm still don't have a very satisfactory explanation for why. It kind of depends on alpha. One thing we noticed was that if alpha is negative, that is more Bergman-y, then the first negative coefficient that showed up was in a later optimal approximant. So for example, in the Hardy space for 2 minus z1 minus z2, our first negative coefficient appeared in the 17th optimal approximant. And in the Dirichlet space, it occurred in the 8th optimal approximant. And in the Bergman space, it occurred in the 47th optimal approximant. So I think it'd be kind of interesting to see, like, could this be quantified? What kind of relationship are we looking at here? And what does this tell us about the spaces? I'm just making a note because I think it's cool. I don't have any solid answers to those questions, but it could be a neat project. But now let's do kind of a flashback, the 1970s. So in the 70s, a bunch of electrical engineers were trying to solve least squares inverse problems. Now, my poor linear algebra students had to hear about all of this last spring because these planar least squares inverses that the electrical engineers were looking at, these are just optimal approximants. And you actually, well, we actually did least squares problems in linear algebra. Well, least squares problems, you're really kind of looking at a Hardy space, right? I'm talking about the squares of these coefficients. And the engineers actually did it in the Bidisk too. That's why this is interesting, because this was done years and years before, like, Manitoba et al. Were looking at it, but they were doing it in the disk and in the Bidisk. Specifically just for the Hardy space, though. They were doing least squares problems. They didn't really care about, say, the Bergman space or the Dirichlet space. And one of the things they were looking at is these reflections of orthogonal polynomials in these weighted spaces, as well as separable functions. And this is pretty similar. If you look, there's a Pacific Journal of Math paper from 2015 with Manitoba, Condori, Liao, Secco, and Sola. They looked at a lot of this stuff for the Dirichlet-type spaces. And the reason the engineers cared is because this was about applications to filtering theory. If you saw Catherine's talk, she went over this a little bit, but roughly what you need to know is that the engineers care because filters are stable, that means like well-behaved, when these polynomials have no zeros in the Bidisk. Roughly what you should be thinking is that the engineers were saying, all right, I want to approximate my function f, but I'm going to look at 1 over f, and then I'm going to look at 1 over 1 over f. And to do 1 over 1 over f, the thing you're approximating, you'd like to not be dividing by 0. So they want to see no zeros in the Bidisk. Now, in the disk, in the one variable case, Benito, Havenson, Liao, Secco, and Sola in 2016 did a thing where they say, okay, well, we can show that in the one variable case, in the Hardy space and other positive alpha, or other non-negative alpha, excuse me, as long as you have f of 0 is not 0, then the 0 sets of your optimal approximants will be outside the closed disk. That is, they'll be 0 free inside the closed disk. And then for negative alpha, for example, for the Bergman space, the optimal approximants will be 0 free outside of a smaller closed disk. So depending on the alpha, that's going to change the radius of the disk you can have. If alpha is greater than or equal to 0, it's just the unit disk. So the engineers had noticed this as well in the Hardy space, and they made this conjecture that we've been calling the Shanks conjecture. And this is, given a polynomial f, the optimal approximants to 1 over f in the Hardy space of the Bidisk will be 0 free in the Bidisk. Now, this turns out to be not true. This doesn't hold. And part of why is because they have no assumptions on f other than that it's a polynomial. In 1975, a pair of engineers, Jenin and Comp, found a counterexample to this. And they said, okay, look, here's a polynomial. Its optimal approximants definitely have zeros inside the Bidisk. This isn't true. The example they chose was a polynomial that had zeros in the Bidisk. So the thing they started with was already going to cause some problems. A side note here, going back and looking at this paper by Jenin and Comp, you really appreciate having living in the future and having our technology. Their counterexample has a lot of very computationally gross numbers in it. They really had to like tweak this. We ended up trying a nicer looking version of their function, of their polynomial, and it still works. It's just they didn't have the computational power to check it. But yeah, Shanks conjecture, it's out. But we could weaken this. We could make it look more like our theorem up here, where we're saying, okay, well, we want to have some restriction on the zeros of our original function. So here's a version that we were calling the weakest Shanks conjecture. There are several intermediary ones. And here we're saying, okay, take an irreducible polynomial, make it have no zeros in the bidisk. Maybe that will give us optimal approximants for 1 over b that are zero free in the bidisk. Now, it turns out this isn't true either in some spaces. Now, in the Hardy space, we don't know. But in the Bergman space, Ellen and I have a counterexample. And here is our function b. Please believe me that this is indeed irreducible and has no zeros in the bidisk. Here is just its P2 optimal approximant. We don't have to go further than this. For the P2 optimal approximant, you kind of squint right down there in the corner. That does indeed go inside the bidisk. That gray line right there is the boundary. What we're talking about here is the facial zero sets. So I'm saying put one of our variables on a circle, and then we're going to plot it as you go around the circle here. Here's minus pi to pi. And you notice that it does indeed go inside the bidisk. And just so you believe me, here are zero sets for our function b here. I solved it for either variable, and you can see those zero sets are safely outside the bidisk. So it satisfies the hypotheses of the weakest Shanks conjecture, but we do have zeros inside the bidisk. We can actually do better. You can dilate b here. I just did multiply by 0.99 by each variable. If you do that, I promise these do all actually are rational numbers. It's just writing them as ratios is actually harder to look at than writing them as decimals. But this is not a like numerical rounding error or anything. These actually are legitimately rational numbers. And I have shown you the zero sets here. What it does is it just scrooches them up a little bit. Zoom in right here. I promise they really are legitimately outside the closed bidisk. My zero sets are away. But when I look at that optimal approximant, recomputing for this one, you see that it is still got zeros inside the bidisk. So in the Bergman space, we're actually able to get something that has zeros outside the bidisk, legitimately outside, not on the boundary, but its optimal approximants still have zeros inside the bidisk. Now, this doesn't work in the Hardy space. Dilated or not, here's the undilated version. Those are pretty safely outside the bidisk, the zeros for the optimal approximants, so we're out of luck there. And in some sense, it's easier, big air quotes, to break Shanks in the Bergman space. So we want to have it be looking at just this same example. I started with the same function b here and computed optimal approximants in the Dirichlet space, the Hardy space, and the Bergman space. And in the Bergman space, you can see, yep, those are inside my bidisk. The Hardy space is further out, and the Dirichlet space is further out. So it seems like, okay, the more Bergman-y you get, maybe it's easier to get your zeros into the bidisk. Again, we don't have this really quantified. This is just a particular counterexample. But another question you might ask here is the Bergman space the line? Is it like anything less Bergman-y than the Bergman space is that going to mean that we have no zeros in the bidisk? And that's not true. If you choose alpha to be minus 0.85, so slightly more towards the Hardy space, this example, we don't even have to change examples. This example still gives a 0 inside the bidisk. So that means the Bergman space isn't the line, and it means that like maybe you could break the Shanks conjecture in the Hardy space. Maybe it's just a matter of finding the right counterexample. And another question someone had asked us at one point is, what happens if you have two different alpha? So one example, again, with this particular function, if you choose alpha 1 is minus 3 and alpha 2 is 0, you're still able to get zeros for this particular example into the bidisk, but of course it won't be symmetric. Our other examples, notice they're all symmetric. That's because the alphas are equal. Here I have alpha 1 is one thing, alpha 2 is another thing. It'll go in on one of the faces, but not on the other. So, but we are still able to get some zeros into the bidisk this way. So I think it'd be interesting to see if you could figure out where this line is if it's not true for the Hardy space. I honestly don't know if you could come up with a counterexample for the Hardy space. The Shanks conjecture might be true there, and that would be something really awesome to know if someone can figure it out. So let's kind of change gears slightly here. I mentioned that the engineers were looking at zeros of optimal approximants, and they were looking at these reflections of orthogonal polynomials. And you remember that, okay, we said hypothetically you should be able to recover your orthogonal polynomials by looking at differences of optimal approximants. Well, here, let's look at this particular example. Here's the f I'm going to look at approximating 1 over. So here I'm doing 1 over 1 minus z1, z2. You choose A appropriately to make sure that you have your 0 on the boundary. Boundary behavior is more interesting, so we like putting zeros on the boundary. And you'll notice that here I've only written P0, P4, and P12. And the reason for that is because P1 is also 1/2, and P2 is also 1/2, and P3 is also 1/2. And then P4, well, that's the same as P5 through P11. So this one only changes when you get to a new power of Z1, Z2. Kind of makes sense. You started with Z1, Z2s here, you should get Z1, Z2s here. But this means that when you do differences of consecutive optimal approximants, you're definitely not going to get all of your orthogonal polynomials. Again, you're not going to be able to build just a Z1 ever. You only have Z1, Z2s. So, okay, let's just do this naively. Let's Gram-Schmidt it. I want to find orthogonal polynomials. Well, I'm going to Gram-Schmidt my monomials with this weighted inner product. And when you do that, this is what you get. It kind of makes sense. You're just getting monomials, and then something weird, and then monomials, and then something weird, and then something weird, and then monomials. So until you're getting up to these new powers, you're basically getting monomials. But notice that this doesn't have a power of Z1, Z2. But there's definitely a pattern here. And if you continue, you'll see again, there's a pattern. Here I'm doing Phi12, Phi17, Phi18. Notice that looks kind of like what we've got with Phi4, Phi7, and Phi8 here. I have basically the same coefficients, and then it's just a matter of a different multiple of Z1 or Z2. Let's examine these more carefully. Let's start with our Phi4, Phi7, Phi8. And this is where my little triangle diagram comes back in. Because if you look at which monomials are included in each of these orthogonal polynomials, you see, oh, look, they all stay in their little row. And then when I go up to Z1 squared Z2, I really am just saying, okay, take this orthogonal polynomial, multiply by Z1, or multiply by Z2. Same thing happens when you look at Phi12, Phi17, and Phi18. Here's your Phi12. Multiply up for Phi17. Notice there's the term you're adding in with your Gram-Schmidt. And there it is. So you multiply up or multiply down. So you're just going in these rows. Now we can actually write a formula for this. I'm looking at a very specific example here. We're looking at 1 minus Z1, Z2, and I'm looking specifically in the Hardy space. The reason I'm giving this as the example here is that these are familiar orthogonal polynomials on the unit circle. And what we're saying is, okay, well, plug Z1, Z2 into it, and then multiply up or down by the appropriate power of Z1 or Z2. And you'll be able to get yourself a nice orthogonal basis. Now, we actually have a more complicated version of this in our paper, holds more generality. Instead of just having 1 minus Z1, Z2, we've got it for grab yourself a polynomial, plug in Z1, Z2, use that as your function, as your weight. And this will just yield a more complicated Rn. If we actually go back, it'll have to do with how long these rows are. And we actually do it in, again, more generality. Here I've written it for just the Hardy space, but we can do it for some reproducing kernel Hilbert space, H of omega. Omega needs to be an open set containing the origin. And in this case, we also require that the monomials are pairwise orthogonal. This is not such a heavy lift. All of our favorite spaces have this. So then we weight it by our function f. We can find our orthogonal polynomials. But what we really see when we look at this is that this is secretly a one variable problem, really. I'm looking at something Z1, Z2s, a polynomial in terms of Z1, Z2s. And the orthogonal polynomials in that weighted space, they just say, okay, well, take one variable ones, plug in Z1, Z2, and then multiply as appropriate. It's not really legitimately a two variable problem. It's just a dramatization of a one variable problem. So there is a nice two variable example that we have. Here, I'm going to write about this in the Drury-Arvidsson space, but it also works in a more general space, and I'll talk about that too. Here, I'm taking, instead of Z1 times Z2, I'm doing Z1 plus Z2. And I have just taken this and run it through the matrix method to compute optimal approximants. Computed the first 5 here. Look how pretty those are. They follow a really nice pattern. But then when you actually look at the optimal approximate, not the optimal approximants, the orthogonal polynomials, these are extremely pretty because they have a really predictable form. If you actually go through and compute a whole bunch of these, you'll see that the first orthogonal polynomial that includes this term here, well, it's going to include exactly the monomials in this little square. So once you know which monomials are included and you know how to deal with your orthogonality conditions, then this becomes not so hard to compute. We can get a recursive formula, because Gram-Schmidt is recursive, to find the orthogonal polynomials. And you can actually get a closed form too, which I think is pretty cool. So here we've got our closed form for the Drury-Arvidsson space in 2 variables. I am looking at this weight with the 1 minus root 2 over 2 Z1 plus Z2. This is to make sure there's a 0 on the boundary. And you can write out exactly which monomials will be included. And there's a somewhat complicated, but in reality, not as bad as it could have been, formula for the coefficients here, my phi hats. And there's a nice formula for the norms as well, the norms squared. Now, once you have the orthogonal polynomials, you can then use these to recreate the optimal approximants. I'm afraid they don't look quite as pretty, but it can be done. And then, of course, this is Bergman space week. So here I am looking the more general case. I'm looking at these H sub gamma spaces of the 2-ball. We found these in a paper by Richter and Sunberg, not Sunberg, Sunkus. And these are just spaces where you take a certain similar reproducing kernel to the Drury-Arvidsson reproducing kernel, and then you weight it by some number gamma. If you choose gamma equals 3, you get the Bergman space of the ball, for example. And this is basically the same. This is the Pockhammer symbol. It's just a way of dealing with having factorials that aren't factorial. If you have, again, gamma equals 3, these Pockhammer symbols here will end up being a ratio of factorials like before. So we have this in some generality for this very particular example. And again, I recognize that it is a pretty specific example. I've only done it for one of them. But it's kind of nice to have a legitimately 2-variable example. Also, I think there's kind of a neat potential undergraduate research project here. This is something I'm probably going to rope an undergrad into doing. In the 1-variable case, if you do 1 minus z to the alpha, you can, or not to the alpha, to the n, you can get nice orthogonal polynomials and optimal approximants. We've seen something kind of similar when we look at this. Like, you can run the things through Gram-Schmidt and be like, oh, look, there's obviously a pattern here. But I didn't go through and sit down and compute the closed form, because at that point it's mostly a Calc 2 exercise. And I think it would be a good learning experience for an undergrad. So probably going to strong arm one of them into doing that. An important point here, though, is that these H gamma spaces, or maybe even just the ball, it's special. If we look at basically the analog of this, where I have Z1 plus Z2 in the bidisk, well, my orthogonal polynomials certainly aren't pretty anymore. They definitely don't have the same nice pattern of which monomials are included. There's definitely still something going on, some sort of symmetry, but I mean, we started with a symmetric function, so who cares? And yeah, it's definitely harder to get your hands on. In the ball, everything is, it's round, it's nice. But in the bidisk, things are going to be much more complicated. But okay, let's go back and remember why we were looking at all of this stuff in the first place. We wanted to bother computing all of these orthogonal polynomials. The reason we bothered was because sometimes you can't find the orthogonal polynomials as a difference of your optimal approximants. We weren't able to find orthogonal polynomials corresponding to, say, like P3 here, because it's the same as P2. And this isn't even the worst case. In this case, we're not going to get all of our orthogonal polynomials, but we'll get some. In some cases, for some functions, you're not going to be able to get any orthogonal polynomials from your optimal approximants. All of the optimal approximants will be equal. These are what we call weakly inner functions. So here's our definition for weakly inner. You're saying it's weakly inner if you take the function and you inner product it with itself times a monomial, that gives you 0. This is, from the name, a weaker version of innerness, of an inner function. And when this happens, all of your optimal approximants are going to be equal to a single constant. So you really can't do any approximation at all. This kind of ties into one of the original reasons people were looking at optimal approximants. People were interested in cyclicity. And well, inner is kind of the opposite of cyclic. So if something is inner, you're going to have a heck of a time doing optimal approximate stuff with it. If it's outer, your optimal approximants are going to be great. Well, weakly inner is this thing where things are going bad. And remember, our classically inner, if something's classically inner, it turns out it is indeed weakly inner. However, this doesn't go the other way. Weakly inner really is a different thing. In 1 variable, inner and weakly inner, they're the same. They are completely interchangeable. In several variables, we have some problems. And we were able to find some explicit examples of functions that are weakly inner, but not inner. So here we're looking at these Shapiro-Shields functions. And I'm looking at it for the Hardy space of the bidisk here. I'm just taking the 1-point Shapiro-Shields function. You can compute it out. It uses determinants to do the construction. And this ends up being weakly inner, but not classically inner. If you go back and look at the Ruden-Stout definition of a rational inner function, then this ends up failing that. So it's definitely not classically inner. And Shapiro-Shields functions can be used to give examples of weakly inner functions in any reproducing kernel Hilbert space. So we know these things do exist. I personally think it'd be kind of interesting to look into them a little bit more. I haven't quite gotten the chance yet, but I would like to see what else we can say about weakly inner, especially because once you're in several variables, this is not the same thing as inner. It's, you know, a weaker version. And it might be interesting to look at some kind of factorization. I know the engineers looked at something kind of factorization here, but not in a ton of detail. And then it's Bergman week. So to talk more about Bergman stuff, I went and grabbed the Shapiro-Shields function for the Bergman space of the bidisk. Here's our 1 point. It's grosser. If you stare at it long enough, you'll realize that it really does legitimately follow a pattern. Like, it makes sense, but it's not nearly as pretty as the Hardy space one. The Hardy space one, you say, oh yeah, I see exactly what's happened here. And the Bergman space one, if you stare at it, you can kind of see it. Everything's squared in the bottom here. And then you can see that this is kind of squared out up here. But it's not exactly the same. So looks like I'll be finishing rather early, but I think that's okay because it's lunchtime. So thank you all for attending. I have kind of a summary. Things are harder in several variables. You've got to choose a monomial ordering. There's some question about, depending on the function you're looking at, the f you're starting with, maybe you would want to choose a monomial ordering to optimize approximating that particular function. And choosing different orderings might end up being useful in applications. And also, in several variables, weakly inner doesn't imply inner. We have our Shapiro-Shields functions, so we don't have that same thing with our cyclicity. And then I just put this in as a note because I think it's weird. Those negative coefficients showed up for even a really nice function, which means that these optimal approximants, they're not coming from just a positive weighting of the Taylor coefficients. We're doing something weird here. And then we also were able to get ourselves a counterexample in the Bergman space to the Shanks conjecture, but not in the Hardy space. We don't know. And there was some discussion as well about, okay, well, we have this counterexample in the Bergman space, but how Bergman-y does something have to be in order for it to break? So, and there's a couple other neat things. We found closed forms for some orthogonal polynomials, which I think is cool. For this case, it's secretly a one-variable problem that worked in both the bidisk and the ball. You can do it in more variables too. I did this in the bidisk and the 2-ball. You can do it in 3 or 5 or 75 variables. It doesn't really matter. It's just that it gets truly disgusting to write out. So 2 is fine. And then we were able to find ourselves a closed form for orthogonal polynomials. We did this way for the ball, but the bidisk, we're still a little lost there. It is nice to have a legitimate 2-variable example though. So thanks for sticking around, and yeah, I'll stop there.
Okay, thank you, Meredith. Let's all thank her for a terrific talk. All right, does anybody have any questions? Either put them in the chat or just shout them out.
Hey, Meredith, I have a question.
Mm-hmm.
So I know you said you were thinking about, you were considering breaking Shanks' conjecture by, say, looking at the Bergman space. I don't, from those diagrams that you drew, did you, I don't remember if you said specifically if you can make a claim that, say, if the optimal approximate is zero free, say in the bidisk, does that necessarily mean it's zero free in spaces above it, like the Hardy space?
Oh, let me see. I'll go back to those. To answer your question, no, I don't think we have a statement to that effect. So I think you're thinking about this thing.
Yeah, because it would be nice, at least if, like, I was wondering if there's some kind of relationship saying, like, if it's zero free in Bergman, it's zero free somewhere else.
I don't know, actually, off the top of my head, but that would definitely be worth investigating. Again, this is a really specific example, right? This is only for one function, and we really like, we're sneaky about picking it, right? So it could be that that works in general. If it's zero free in the Bergman space, you're set for all of the alphas bigger than that. But I don't think this shows that. This is a very, even calling it qualitative is probably too precise, but yeah.
Because that was interesting. I was thinking, okay, so it seems like you're going down to break Shanks, but maybe it would be worth looking at going up to, up in alpha and try to confirm Shanks. So maybe there's a space. It doesn't seem like it would be easier than the Hardy space, but maybe in this case, it would be easier to work with, where you can verify Shanks' conjecture is true in that particular space and somehow relate it down to the Hardy space.
Right. Well, so like, I think you're thinking it might be easier to prove it's true in like the Dirichlet space, for example, and then
something like that.
Yeah.
I mean, I don't know. I haven't looked at optimal approximants in any other space, but I mean, I think, at least in, I don't know. I think it would be interesting to see if maybe that route is doable.
I also think that would be neat. That's part of why I put this up here, is because I think that like there's something here. I just haven't looked into it in detail. So you can do it, like totally let me know. I'd be interested.
Yeah, no, it's definitely something that at some point in my life I want to settle, but who knows? Could take 30 years.
Okay, all right. I think I'm gonna jump in here with my own question. So stick on this diagram, Meredith. So A2, it seems like it intersects something smaller than, so the optimal approximate has an extra 0. I think that's what I'm interpreting Shanks' conjecture says, right, for the Bergman space. And it also seems like you can adjust the coefficients, right, so that you can make it intersect the bidisk a whole bunch of times. So for example, in the disk, so I'm new to optimal approximate, so, but I know in the single variable case, I think in H2 or something like that, the extra zeros have to lie outside the disk. Any extra zeros have to lie outside the disk. But in the Banach space case, you can actually fill out regions inside the disk. So in several variables, can you choose an F? So can you find a domain inside the bidisk, so that when you're in that domain, you can choose an F, and then you wait long enough for an optimal polynomial to have an extra 0. Is there a version of that in the several variable thing?
Not that I know of. I haven't looked at like the Banach space stuff. One of the things when Ellen and I were first looking at this, we were thinking about is, okay, so we got zeros into the bidisk for the Bergman space.
Right.
But like in reality, that's not so surprising maybe, because in the one variable case for the Bergman space, they were able to get zeros into the disk, right? It's just there was a slightly smaller disk that you couldn't get zeros into.
Right. But but the question is, can you fill out? So and the question is, can you make Shanks conjecture a complete disaster? In other words, can you fill out everything? Can you?
Oh, yeah,
So
yeah.
if you give me a point outside a smaller disk or whatever you want to call it, then your job would be just to produce a function in your Hilbert space, whatever it is, of several variables, and then wait long enough for a large enough n for an orthogonal polynomial to have an extra
Right, so
zero there.
the game where you say, okay, here's a point, find me an optimal approximant that has a zero there.
Right.
Yeah, I don't know, actually. One of the things we noticed when we were doing this, so I've just shown you guys the P2 here. This is actually because for this example, and again, this is one example, so maybe you can come up with a more clever one, but for like P3 even, or P5, there were not zeros inside the Bidisk.
Okay.
So I don't know if it's necessarily a degree thing. It could, again, just be weird behavior for this particular example. And again, I think you were saying, looking at this in the Bonnet space, we didn't look at that at all.
Right.
So yeah, maybe there's something else that can be done there.
All right. So I think I dominated too much time here with question.
Oh, you're fine. We have plenty of
Does
time.
anybody else have a question or comment or? All right.
Oh, there's a question in the chat. Can you say anything about the locations of zeros of the optimal approximants for 1 over f, with f is 1 minus z1, z2? Alan, correct me if I'm wrong, but I don't think we actually talked about this. I'm trying to remember. I don't think we said anything. I think you probably could. We have a form for the orthogonal polynomials, right? And you could hypothetically then use those to rebuild your optimal approximants, and then maybe you could say something. I am pretty sure we know they're outside the disk, but that's not terribly informative, or outside the Bidisk.
All right. Any other comments? I always hate these awkward things where you're trying to keep track of everything and the chat. Okay, so otherwise, let's sort of head to lunch or wherever we're going, wherever we are in the world. And let's thank Meredith again for a very informative talk.